Okay, we complete our reasoning. We've concluded that the equations are solved at x, y, z each equal to 1/3, and that gives us a value of lambda that we could easily enough evaluate. 1/3 squared is 1/9, so we have 1 and 3/9, which is 4/3. So this is going to be 4/3 to the 3/2. Each of these is going to be 1/3, so lambda is going to be 1/3 divided by 4/3 to the 3/2. There's no point right now in evaluating that. The only thing that I'll say that should be fairly evident is that since this expression is positive, its 3/2 power is positive. Since x, y, and z are all positive, then these numbers are all negative, which means that the product of lambda with a positive number is a negative number. And the one really relevant thing then we determine about lambda is, from our solution, x, y, z equals 1/3, 1/3, 1/3. It's easy to see that lambda is less than 0. What does that tell us about whether we have a maximum or a minimum? Now recall that our condition is that del T equals lambda times del F. So del T is in the direction opposite del F. Now, del F, you recall, is just xi plus yj plus zk. Xi plus yj plus zk is a vector directed, and I've got a mistake, this is directed radially. It's not radial because we don't have the x, the y, and the z. Hang on a minute. I wrote this down without thinking, always a bad idea. Remember that f of x, y, z was x plus y plus z minus 1 equals 0. The gradient was just the obvious. We got x plus y plus z minus 1. That's our f of x, y, z. The gradient's just I plus j plus k. So the gradient is I plus j plus k at the point 1/3, 1/3, 1/3. This is radial. Away from the origin. Now the fact that it's radial isn't, well, it's important, but in determining whether this is a maximum or minimum point, we simply note that this gradient vector for f, the gradient vector that we used to obtain the equations corresponding to del T equals lambda del F, is pointing away from the origin, so that since lambda is negative, this lambda del F is pointing in toward the origin. So lambda is less than 0 implies that lambda times del F is radial toward the origin. And this, in turn, being equal to delta t, implies that delta t is radial toward the origin. Now the fact that it's radial toward the origin, again, is important, but in general, what does this tell us about, first of all, whether the temperature is maximized at this point, and secondly, how do we use similar calculations and similar reasoning to determine for a more general, more complicated function where we don't already know that delta t is radial toward the origin, where we really don't have a good handle on maybe either of these functions. Okay, on second thought, we probably don't want to go that deeply into this interpretation to determine just how the lambda, del f, and del t can be used to determine whether you have a maximum or a minimum. Although that's a question well worth considering, so you might want to think about it. Just in interest of time, though, that would take us a little bit astray from our main purpose here, which is to learn to use this general method. Now the temperature function, remember, T of x, y, z is extreme at 1/3, 1/3, 1/3, where the temperature is 1 over the square root of 1 plus 1/3 squared plus 1/3 squared plus 1/3 squared, using our original temperature function 1 over 1 plus x squared plus y squared plus z squared. So we can evaluate the temperature at this point, and that's going to be 1 over the square root of 4/3. So it's going to be the square root of 3/4. Turns out that's going to be square root of 3 over 2, which is approximately 0.87. This is the only point at which these two vectors are parallel, in which one of the vectors is a multiple of the other. So it's the only point at which we can have an extreme value on the plane, x plus y plus z minus 1 equals 0. This means that as we move away from this point on the plane, that the temperature is either increasing or decreasing. Now, clearly the point 1, 0, 0 is on the plane x plus y plus z equals 1, and I've got the 1 over on this side instead of this side, but that's perfectly okay. And the temperature at 1, 0, 0 is what? It's 1 over the square root of 1 plus 1 squared plus 0 squared plus 0 squared, which is the square root of 2 over 2, which is approximately 0.71. This shows that the temperature at least one point of the plane is lower than the temperature at the extreme point. There's only one extreme point, so that the temperature at the extreme point is therefore a maximum. It's greater than the temperature at some other point. The temperature always goes in the same direction when you go away from this point. Since it's going down between here and here, it's going down everywhere as you move away from the point 1/3, 1/3, 1/3 on the plane.